Hey everybody, this is Dr. White here with something out of the section where they try to prove the central limit theorem as much as we're capable of at this level of things. I am going to essentially repeat that proof but offer a few more details. Starting out, I want to say this is something you're going to be most comfortable with if you've already had real analysis like Math 431. Preferably also Math 432 to be really comfortable. But if you've only had Calc 2, you can still follow along and there'll be parts that you'll have to take on faith. But it's a really good idea to follow along and to read it several times and then read the book and see if you can be convinced of as many of the steps of the proof as you can. So starting off, I want to begin with a lemma. A lemma is just a math theorem that's going to be mostly used to prove some other theorem that you're primarily interested in. This lemma is right here. Suppose you've got a sequence of real numbers yn, y1, y2, y3, y4, and so on. And suppose that yn approaches 0 as n goes to infinity. Then for any real number r, the limit as n goes to infinity of 1 plus rn plus yn over n to the n is just e to the r. This should look familiar to you. We already know from using L'Hopital's rule in calculus that the limit of 1 plus r over n to the n is e to the r for any real number r. And this expression up here is very, very similar. It just it's got another little bit added onto it, a yn over n. And that little bit is a little bit because the yns are going to 0. So not only is the n on the bottom going to infinity, but the yns on the top are going to 0. So what you're adding on is really tiny compared to the 1 and even compared to the r over n. So it seems intuitively possible that it could end up converging to the same thing as the more familiar quantity. And the book just claims that it does, says it's a result in advanced calculus that it does. And I'm going to go ahead and show to you why it converges to the same thing. So we will be using this fact pretty soon. Okay, let's let epsilon be an arbitrary positive number. It could be as small as you like, but it's got to be positive. Okay? Well, since the yn sequence converges to 0, there's got to be a positive integer n sub epsilon that's big enough so that for all little n's bigger than or equal to n sub epsilon, the yn is within epsilon of 0, meaning that yn would be between minus epsilon and epsilon. And you can also make that n epsilon big enough so that for all of the little n's bigger than it, r minus epsilon over n is not too negative. In particular, I want it to be bigger than -1. So like if epsilon for some reason were bigger than r, that would be a negative number. But if I divide it by a big enough n, then I can get that total fraction to be not too big a negative, and I can make it bigger than -1. Okay. So given that n sub epsilon, and assuming that our little n is at least that n sub epsilon, let's see what happens. Well, because of this bit, the expression in the parentheses, whose limit we want, the expression inside the parentheses, that'll have to be less than this. That's where you stick in an epsilon instead of yn and get a little bit bigger. And it has to be bigger than this. But because of the way we set up things, this is bigger than -1, so this is still a positive number. And so these numbers here, these three quantities here, they're all positive numbers. Now, let's raise all three of them to the n. Because raising to the nth power is an increasing function when your base is increasing, then we know that this middle thing really is bigger than this, which in turn, but on the other hand, it's less than this. And this middle thing is the thing whose limit I want to find. Okay, well, when I look at this, I see that what I've got on the top of the n is just something that doesn't change as n changes. It's just r minus epsilon. And so because of this L'Hopital's rule fact up here, I can just use an r minus epsilon instead of the r and get that this has to be converging to e to the r minus epsilon as n goes to infinity. Okay, and similarly, this has to be converging to e to the r plus epsilon. So what's going on in the middle here is going to have to be trapped in between those two real numbers, e to the r minus epsilon and e to the r plus epsilon. So if its limit does exist, its limit would be in between here and here, okay? We would have this going on. And it would be going on for any epsilon bigger than 0 as long as the little n is bigger than the n sub epsilon. So no matter how small epsilon is, as long as your little n is big enough, then you can get that to happen. You can get a squeezing to happen. Now, you might say, but wait, Dr. White, how do we know this limit exists? And the fact is, we don't know this limit exists, not yet. But if you're worried about that, then think back to real analysis. Let me move my face a little bit. Just think over to real analysis here in the kind of this parenthetical material. You can read it. Actually, all you really know is that the lim inf and the lim sup of this expression are in between these numbers. And so for those who haven't met lim inf and lim sup before, the lim inf is basically like if you look at all the subsequences of this sequence and find the smallest possible number that any of the subsequences could converge to, that would basically be the lim inf. And if you looked among all the subsequences that converge and you look for the biggest possible number they converge to, that would basically be the lim sup. The lim inf would still have to be less than this, and the lim sup would have to be less than this. And so the lim inf and the lim sup are trapped in between the two. So think that way if you're more of a person who's had real analysis. Okay, so remember, this is good for any epsilon, okay? And so we've got this limit here, or if you like, lim inf and lim sup stuck in between. And it's stuck in between here and here, no matter what epsilon is, right? And so let's let epsilon go to 0. No matter how close it gets to 0, the limit is stuck in between these two numbers, but this would be going to e to the r, right? And this upper bound is also going to e to the r. And so this poor old limit, or the lim inf and the lim sup, they're stuck between two things that are getting closer and closer to e to the r, so they have to go to e to the r. The limit really does have to exist. The lim sup and the lim inf have to really come to be the same thing, and then therefore that's the limit. So we've got this, and like I said, you do need to have studied a little real analysis to really be on firm ground there. Also, officially, you know from Calc 2, although people never get enough practice with it, Taylor's theorem. And Taylor's theorem says take a function f of x and suppose it's differentiable n plus 1 times, which means all its derivatives up to the n plus first derivative at least exist. Then for any x, any real number x, there exists a real number c sub x, because it depends on x, that's somewhere between 0 and x, so that f of x could be written like this. This first bit is a polynomial in x, okay? Going from the 0th power, which is right after the f of 0, first power, whose coefficient is f prime of 0, second power, the x squared there, coefficient is second derivative at 0 over 2 factorial. And it keeps going with that same pattern, ith derivative over ith factorial at 0, up to nth derivative at 0 over n factorial. That's the polynomial part, plus what they call the remainder. And that's the n plus first derivative of f at this mystery number cx that's in between the 0 and the x, times x to the n plus 1 over n plus 1 factorial. So Taylor's theorem was this thing that said that basically any differentiable function is a glorified polynomial. It's exactly a polynomial plus a little bit left over. We're going to apply this for the case n equal 1. Imagine a function that's differentiable twice to a second derivative. Then you could write f of x. For every real number x, you could find a cx so that f of x could be written as this linear function, f0 plus f prime of 0 times x, plus this little remainder that uses the second derivative at cx times the x squared over 2. Okay. Another little warm-up thing before we get on to the proof of the central limit theorem. We're just going to offer this up without any proof at all. The book does the same. Suppose you got a sequence of random variables, y1, y2, y3, all the way up to yn and yn plus 1, and so on forever, okay? A sequence of random variables. Well, then you would have a sequence of moment-generating functions, if they all had moment-generating functions anyway. Now, suppose that those moment-generating functions converge to some one function, okay, of some that is a moment-generating function for some random variable y, okay? So suppose your moment-generating functions converge to something that's the moment-generating function for some new random variable y. Then guess what? The distributions of the y-ends have to converge to the distribution of the y. The y-ends have to look more and more like y as n goes to infinity. This is going to be the key to the central limit theorem. What we're going to do is for the y-ends, we're going to use the standardizations of the sample means. And we're going to show that they converge to the standard normal by showing that their moment-generating functions converge to the moment-generating function for a standard normal. That's going to be our basic strategy. Now, if that's going to be our strategy, then we should kind of look at these standardized sample means. So consider this expression here. Now, I am defining that xn bar. That's the sample mean based on x1, x2 up through xn. Okay, it's based on that random sample up through size n. Now we know that that has an expected value of the mean of the underlying random variable, which we'll be calling mu, and it has a variance equal to the variance of the underlying random variable over n. Call that variance sigma squared. Then the standard deviation of the x bar n would be sigma over root n. And so this expression here is the standardization of the sample mean based on a sample of size n. We're going to call it Wn for short, and we're going to be studying the limit of the distributions of the Wn, hoping that it comes to a standard normal. Okay? That's what the central limit says. And so like I said, we're going to be hoping that we can show that the limit of the moment generating functions of the Wn come to e to the t squared over 2, because that's the moment generating function for a standard normal. Remember, for a normal, moment generating function is this: stick in mu equals 0, stick in sigma squared is 1, and you do get this. So here we go. We're really launching into the central limit theorem now that I've given you some tools and told you my basic strategy. Let's get into the proof. So I take this Wn like it's defined, and I just do a tiny bit of algebra to write it like this. Oops. Okay. And then I stick a root n divided by a root n onto things. So I'm multiplying by 1. I'm not changing the value of anything. So there's an n right there on top, okay? And I'm going to multiply that in right here. And so I'll have n times the sample mean minus n times the mu over root n sigma. Now, by definition of the sample mean, n times it would just be the sum x1 through xn. Okay? So we'll focus on that for a moment. The Wn can be written like that. And so when we try to get the moment generating function for Wn, e to the, or expected value of e to the twn, we're going to be writing the Wn like that. And so you can see up here, I've done that. Here's the top of the Wn, here's the bottom of the Wn, and we got to put the t somewhere, so I stuck it right there. Okay, now I could certainly multiply that t over root n sigma in through the sum sign. And so I would have e to a sum, okay? And by a property of exponentials, that's the product of e to the summands. And so if you stare at those different summands, you'll see that, yeah, they would add up to this very sum that you see here. So the move from here to here is just a property of exponentials. But remember, the x1, x2, x3, x4, and so on, they're all random samples from the same distribution. Random sample, part of the definition of that is they're independent of each other. The xi's are independent of each other. And these little guys, this versus each one of the others, each one is built on its own xi. And so they are independent of each other, okay? And so since these e to the powers are independent of each other and you're taking the expected value of them, well, remember the expected value of a product of independence is the product of the expected values. So that's what I'm doing when I move down here, okay? Now, all the xi's also have the same distribution. They're all that same underlying distribution, x. Therefore, all of these random variables, this one and all the way up to this one, all have the same distribution. Therefore, they have the same expected value. Therefore, all I got to really do is take one of these and raise it to the nth power. And so really, I'm just looking at the moment generating function for, like if I'm looking at that one right there, I'm looking at the moment generating function for x1 minus mu over sigma at the value t over root n. Okay, I could just as well easily say the moment generating function for x minus mu over sigma, since x1 and x2 and x3, they all have that common distribution x. So I'm going to do that. So looking to see what does this converge to, but what we've got so far is that this can be written like this. Okay. Now, that's kind of a mouthful to write, and so I'm just going to write it little m for short. Moment generating function of the standardization of the x random variable, just write it as little m of real numbers. Also remember, you know, for moment generating functions to exist, there has to be this interval around 0 where the expected value is well defined. So there has to be some h bigger than 0 so that for all the t over root n's between minus h and h, that this is well defined. Okay. So what that h is, it depends on what x is, but since we're assuming the x has a moment generating function, there is such an h, and so we're going to be fine. Okay. Now, looking at that x minus mu over sigma, whose moment generating function we're looking at there, we know that it has mean 0 and variance 1 because it's the random variable minus its mean over its standard deviation. And I'm just going to call that y for short in case I have to refer to it again. Well, remember how you can get the mean from the moment generating function by doing n prime at 0. Okay, so n prime of 0 is 0. Also, by the way, just think about the moment generating function at 0. Like, what's that? You may have noticed this already. So it would be the expected value of e to the 0 times, your random variable. And I should have written in there, that should be a y, not an x, a y. But whatever it is, e to the 0 times it is e to the 0, which is a 1. Okay? And the expected value of a constant is that constant. So m at 0 is a 1 for any random variable x. Oh, that's not a mistake. So I'm just claiming it for any random variable x. So that would include the y up here. Okay. So using those two little factoids, the m of 0 is 1 and the m prime of 0 is 0, plus the Taylor's theorem, the thing up here, we can rewrite the m of t just like Taylor's theorem rewrites the f of x. Okay? It can be written as m of t. Well, it can be, you can do this. You can say, okay, there has got to be some number, and I'll call it t1, that's between 0 and t, okay, such that m of t is m of 0 plus m prime is 0 times t plus m double prime at t1 over t squared. So for every t, you can get a t1 that does that. Now m of 0 is 1 and m prime of 0 is 0, so you really only have 1 plus m double prime at t1 times t squared over 2. That's what m of t is. Now I'm going to rewrite this slightly. I'm going to throw in a t squared over 2 and subtract the t squared over 2 right here, so I'm not really changing anything. And so that's how m of t looks. And you can see why I'm doing that. That L'Hopital's rule doohickey had a 1 plus r over n, kind of thing going on here. And maybe I'm just trying to like get something a little bit extra going. Let's see what happens. Well, if this is what m of t is, what would m at t over root n be? Okay, well, for any t over root n, there's going to be a t1 somewhere in between t over root n and minus t over root n. I'm sorry, but t over root n and 0. So that this kind of stuff happens. But if I put in t over root n for a t, I'm going to have a t squared over n right here. And I'll also have a t squared over n right here. So that'll come out like this. Okay. Now remember, that's going to happen as long as the t over root n is between minus h and h, which puts the t between these two real numbers. And of course, the t1 has to be between 0 and t over root n. So strictly speaking, the t1 depends on n. So I really should be calling it t sub 1n to indicate its dependence on n. The book doesn't do that. I think they should. I'm going to start doing that now. So in this expression here, where I'm just taking my previous equation and raising both sides to the n, I'm also sticking in t1n for the t1. Okay, so the moment generating function to the nth, which is what the moment generating function for wn was, it's this expression here. Great. Okay, next little step. Do y'all remember that when the derivative of a function exists at a point, the function has to be continuous at that point? Well, our random variables have moment generating functions. Wn has a moment, the y random variable has this moment generating function, little m. And moment generating functions they've got to be infinitely differentiable. We were taking their derivatives when we first met them, and there was no stopping. It was always defined. So that means the third derivative of m exists, and the third derivative at 0 would therefore exist as well. Therefore, the second derivative would be continuous at 0. And to be continuous at 0 means that if you look at the limit of a function as your variable goes to 0, that limit is the value of the function at 0. So a little thing we know about the second derivative of m is that the limit of m double prime of t as t goes to 0 is m double prime of 0. We also know something about m double prime of 0. Turns out it's 1. And that's because the variance of this y random variable, the x minus mu over sigma, is 1. And remember, variance is the second derivative of the moment at 0 minus the square of the first derivative at 0. The first derivative at 0 is 0. So we're just looking at second derivative of 0 is 1. So yeah, really, that limit's 1. So let's just keep that in mind. You make your t small, m double prime gets closer and closer to 1. So let's think about that t1 sub n as n goes to infinity. The t1n is somewhere in between 0 and t over root n. So t1n is going to 0, right? Therefore, what would this expression have to be doing? Well, the m double prime of t1n would have to be going to m double prime of 0, which is 1. And so this product is going to 0. So even though the t squared isn't changing at the moment, the t1n is what's changing, that's all going to 0. Great. So looking back at this expression here, we've got a 1 plus an r, and the r is a t squared over 2, divided by an n, plus a yn, this stuff over 2, divided by n, all raised to the nth power. We're in the situation of that lemma. It's going to have to converge to the same thing as what this to the n would have done. And so that's converging to, well, let's see. This to the n converges to e to the t squared over 2, the L'Hopital rule fact. So we've done it. We found the limit of the WNs. It's e to the t squared over 2. And that works no matter what the t was. Wow. And that's the moment generating function for standard normal. So the WNs, the standardizations of the sample means, do converge to a standard normal like we wanted. We've proved the central limit theorem. With some further cautions. The central limit theorem is stated in the book when you first meet it as applying to any random distribution, any random sample from a distribution that has a finite mean mu and a finite variance sigma squared. But actually, in order to apply all this proof here, you need that your distribution possesses a moment generating function, which is a stronger assumption. Not all random variables with finite means and standard deviations have a moment generating function. So this is really an early version of the central limit theorem. I believe its proof was probably known sometime in the 1800s. But the proof of the central limit theorem, as stated in the book, early on when we met it in section 5.6, I don't think that was done until 1927 or so. I think it was a Russian mathematician named Levin who managed to do it. So quite a feat, the central limit theorem. Hope you enjoyed this. No particular homework that I know of coming off of this section, but really good idea to look through this, this quite involved proof a few times. That's all for now. See you another day.